Okay. I'm now recording it. So the question was about Cengage, about WebAssign. Okay. And our college participates with Cengage on this program they have called Cengage Unlimited, meaning that a student can purchase for one price all the Cengage books they need for that term. And it's relatively cheap, usually cheaper than any one book would be. But they get only the ebook and, of course, WebAssign, which, of course, is pretty cheap, because it's all electronic. It's not anything physical. Um, you can rent a hard copy, but it's loose leaf, that type of thing, for a really small amount, something like $8 or something like that, if you actually want a physical copy. But for people who are depending only on the ebooks, now I don't know if they're still doing this or not, but originally the only way the student could access the ebook if they had a WebAssign account, a class key. So that meant we had to use WebAssign. Now, have you used WebAssign before in other classes? Okay, did you enjoy it? Was it good? Was it beneficial? Be honest. Huh? Very average. Okay. My experience with it was, and they may have improved it greatly since then, but when they first started pushing us to use it, I spent more time with students trying to explain to them how they had completely correct answers, but they had been told by WebAssign they were wrong because WebAssign's only looking for one specific answer written in one specific way. So it turned out that if the student had it right but just didn't get it in the form they wanted it, they were told it was wrong. And then the student, of course, would think they had done something wrong and would go back and try to redo the problem and probably try some things and do things that were completely wrong and get themselves so totally confused in the subject that it wasn't worth, I found it wasn't worth doing. So I didn't use WebAssign, even though they pushed us to do it for years or however long they were pushing us to do it, until they came along with this Cengage Unlimited, and then they required us to have a WebAssign account. So I just went to the Cengage guy who was pushing that also. I said, look, I don't use it. And I told him why. He said, I understand. I said, but I have to have it. Do you set up course? Yeah, we can set up a course for you. So that's what I've done ever since. They've gone to Cengage Unlimited. They email me, say, what are you teaching? Which one of these books are Cengage books? I explain to them. I tell them the chapters we're covering, all that kind of stuff. They set up the course. I haven't even looked at the courses because I'm not using it. Now, I'm not saying it's not a good product. Okay, I think they have good tutorial, they have good homework exercises, practice problems and stuff, but with that caveat, they're looking for one and only one correct answer. So therefore, I don't want them telling me the student got 3 out of 7 right when they actually got them all right, and I enter that as a grade for them. That's not right for the student. So it's out there for your viewing pleasure, for your benefit, for you to use however you want to use it. Practice doing problems. If you are having trouble with them, send me the problem and I'll let you know whether you're doing it right and they're just not getting the answer they're looking for, or if indeed you're making a mistake. I'll be glad to work with you on that using that. I think they have good tutorial. They have, I back when I was looking at it, they seemed like they had good support material out there. Use it to your heart's content. Um, it is decent stuff, like you said, average. Okay, so I don't know if that was probably way more of an answer than you were wanting. Did that sort of answer your question? See, I didn't set due dates or anything else on there. They did it all. They chose the problems. They did whatever they did. It was done by the guy at WebAssign, not by me. So there is no due date as far as I'm concerned. What due date did they say they were all due by? Okay. If you turn in a whole term's worth of stuff at 10 o'clock on June 31st, it will sit there. I'm not going to do a thing with it. Okay. So uh, I would say take advantage of that to your best advantage. Work the problems, work through it. If you're finding something that's tripping you up consistently, then get it to me and we'll go through it. That is the whole, well, the main purpose of it. So if you are using the ebooks, you can have access to them. Okay. The secondary purpose would be just more practice problems than they have in the book. And if you are running into a consistent difficulty, let me know and we'll work through that difficulty. We'll do it in class. We'll do it individual. We'll do it during office hours. Whenever you want to do it, we can do that. I would say let's do it in class because the odds are that somebody else would probably be having the same problem if they had done that problem. So, but if you want to do it one-on-one, we can do that as well. Did that kind of answer the question? Okay. Any other issues, questions, concerns? Great. I'm glad you asked that. I didn't even know they put due dates on the thing. So um, it's interesting to know. I've learned something this morning. So I'll know if I get a whole bunch of stuff in at the end of the term, it's just going to trash. Okay. It'll be nice to know you did it, but I'd rather you let me know you're doing things as we go rather than at the end. All right. Well, I guess this may be what we're getting this morning. Um, uh, Billy's usually here and Dawson's usually here. So they may both be coming a little later. Ricky has been here some, so that's just about it then. So let's go and get started. Now, I've been having enormous difficulties with the Screencast-O-Matic. I don't think you can see the little icon in the corner. It's a red dot with a counter next to it that says 721, 722. You can't see that lower left corner. Did you see my cursor, the arrow going around in a circle? Okay, can you see the red dot with the timer next to it? That's what I'm circling with my cursor. You cannot. Okay, that's what other classes have told me to. I was going to say that's an indicator we're recording. Okay. Now, I had an old Fujitsu computer I had used for years. I recorded all my classes. Um, it had a writable screen. It had an ionizing pen. It was a tablet computer. It was great for teaching. I used it in class. When we got kicked off campus because of COVID. Um, I continued using it. It was fantastic for doing virtual classes because I used Screencast-O-Matic and sent the files to YouTube. And by the way, for those of you who missed the first day of class and the subsequent classes, they're all, well, mostly out there on YouTube videos. And here's why that's mostly. That computer died. It died once, just a few weeks after we had left campus. And I ordered a new adapter for it because I thought that might be the issue. Ordered a new um, battery for it because I knew the battery was weak. It had been weak, but I always kept it plugged in. Um, we finally got it. It was a long, terrible saga. FedEx said they delivered it, but not to our front porch, to somebody else's, if they delivered it at all. FedEx has been very unreliable in our neighborhood this whole spring. I hope none of you work for FedEx. I'm bad mouthing, but it's true. They have been terrible. Um, and we never got it from it. And their attitude was just reorder it. Well, we did immediately as soon as it didn't arrive. But of course, it was supposed to have arrived on a Friday, and the company didn't get the order until Monday morning. They sent it out immediately. This time, UPS, and UPS was actually a day early getting it, which is good. Once I got the adapter and the battery, got it installed and everything, computer worked like a charm, just like good old times. for about 4 days and then died again. So there was something inherently wrong with the computer. It didn't come back. I couldn't do anything to get it to come back again. So I asked them if they, of course, they didn't have any more of those. They only had three to begin with. And I had had one that died on me. They gave me a second one. Someone else had the third one. It had died a long time ago, too. So anyway, they didn't have any more of those. So they sent me a new, not new, relative new, 18-month-old HP, but it didn't have a writable screen. And I asked for them to put Screencast-O-Matic on it. I asked for them to put WordPerfect and just a few things like that. They sent it to me. It took them a while, but it finally got here, and it was locked, and I couldn't get into it. So what good was it? So I let them know that. They said they would swap it out. They would get me a different one with everything loaded, and they hadn't loaded any of the stuff on it anyway that I'd asked, including Screencast-O-Matic. They said they would get it to me. They never did. I finished the term with an old computer we had here at home. My wife had re energized, you might say, put on new operating system, all that kind of stuff on. So I was able to finish the term, and in between terms, they finally came and picked up that computer, took it back, unlocked it, and put the stuff on that I wanted, sent it back to me, and it operated for about a week and a half, and then the memory started. It was filled. I was doing the same thing I had done with that old Fujitsu, and now the memory would fill up, and I couldn't do Screencast-O-Matic. So that's why I say most of what we did is on Screencast-O-Matic. I can't remember for sure if this class we lost any or not. Since it's first class in the morning, I think probably everything out there is okay. But even if it's not, I'm leaving stuff out there from previous terms when I did have the writable screen, so you don't have to, and those who haven't been here, I've been working problems like this. This is our class, but writing on a piece of paper and holding them up to the camera so you can see what I've done. Well, my last class that I was in, that we were doing that, he said, "Can't you do on a screen?" And he told me someplace that had a screen. I said, "Well, um, Zoom has a screen, a whiteboard." But I said, "I have to do it off the keypad." He said, "Yeah, well, this one I'm talking about does too. It's terrible. I'm going to start today doing that. I've gotten a little better at it than I was before, but if it gets too bad and you'd rather I go back to the piece of paper in front of the screen, in front of the camera, I'll do that." But I found out this other thing about this HP. Other students have told me anytime I turn my head to look at the book, the microphone doesn't pick up well. Did you just notice that? When I turn my head and talk away from it, can you not hear me? Say again? It cuts out. The old Fujitsu, I don't know what it had in it, but I could walk around the classroom. I mean, not the whole classroom, but anything in front of the computer, it picked it up. Now, here's the other thing. Does it cut out when I hold a piece of paper in front of the camera? Did you hear it cut out then and come back? Okay. The last class said that as soon as I held the paper up, they couldn't hear me anymore. So they may have been, say again, the textbook. Okay. Okay. Well, they were telling me even when I held up a piece of paper, we can't hear you. And you could hear me all that time, huh? Okay. Well, I think they were just complaining. I don't, no, I didn't say that, did I? So anyway, I'll try the whiteboard. If you find it unsatisfactory, since you've had them both, I'll go back to the um, writing it on paper. Now, here's the other issue. I don't know if any of you have looked at the videos, but in the video, I'm assuming, at least on my computer, the my picture is a little bitty box at the top, and that's all you got. And when I hold up the paper, all the writing's in that little bitty box. Is that right? Oh, you have it. Okay. Okay. I don't know how it looks on your end. So if you can see and read that, I assume that's being stored in the video. I don't know that for a fact. If any of you have looked at them, tell me, could you read what I was writing there? I know that when I do the whiteboard, I sure hope that's being recorded because that's what's being projected on my screen. So anyway, you let me know which way you want to go, whether you want to go with a piece of paper held up in front of the camera or if you want to go with the whiteboard. So let's go with it. Any other questions or issues before we get started? Sorry I've wasted that much time. None? All right. We are in Chapter 1, Introduction to Differential Equation, which is a lot of blah, 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 but it is somewhat useful blah, 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 because it gives you the idea on the nomenclature, the verbiage, the way of expressing things, what these words mean. Uh, so that's mostly what this chapter has been. We haven't solved the single differential equation. We have verified differential equations, which is an important step as well, but we haven't solved the single differential equation. We're today starting in 1.3, which is the last section in Chapter 1, and this is differential equations as mathematical models. If you have a text, this is on page 22. I understand that some of the ebooks don't have page numbers on them, so it's section 1.3 if you can find that. Okay. Now, this is another blah, blah, blah section, but because it does give you an idea of the range, the scope, the variety of ways that you do use differential equations. That's what the whole purpose here is. And they're calling these mathematical models, which is probably a good statement. Now, again, I've got the book over here to my side. When I turn my head to look at the book, am I cutting out some? I can move the book and put it right on the screen, so I'm now facing the screen always. I mean, put it on my computer, but sometimes it tends to push buttons. This one doesn't seem to be doing as badly as the one yesterday did. Which is better? Book in front of me, to the side, or does it matter? Anybody? Once I start using the whiteboard, I've got to move it to the side. So you're all right with it at the side? Okay, we'll go with it. All right. What a mathematical model is a set of mathematical equations that tries to replicate or identify what's going on in a real world situation. Okay. Now, we're going to be looking at several models. I don't want to go into great detail of everything they do here. They have a nice little thing. I know this will block my voice, so I'm not going to say it in case any of you don't have books. Actually, you might. Can you hear me when I'm hold the book up like this? Oh, you can. Okay, I'm talking underneath the book, and that shows sort of how these models work. Okay, you come up with an idea, you try to come up with equations that you think probably will work. You test them out. If they don't work too well, you try something else. It's basically scientific method, in mathematics. Okay. Um, so if you got your book, hopefully you do, you can see that. Let's go to one of the earliest, I guess, I don't know for sure, but at least it was a long time ago, applications of this. And this was done by Thomas Malthus, a clergyman, English clergyman, and economist, by the way, as well, 1766 through 1834, right about the time we were breaking away from England and forming our new government and stuff. That was when he lived and worked. I don't think he was involved with the earlier part, but he modeled population dynamics with differential equation. And it kind of makes sense. So I'm going to do a couple things here. First, I'm going to expand to a full screen. So I'll lose a lot of things at the bottom. And by the way, if you see someone trying to come in, let me know, because I have so many applications open, Screencast-O-Matic and this, I won't always see it. Okay, I might or might not. So I'm going to now go to the whiteboard, and you'll see it's really pathetic. Okay, and there is a way to do it with text. I don't know. Do y'all see this board at the top? It says select, text, draw, stamp, spotlight, erase, eraser, format, undo. Do you see that taskbar at the top? No, you don't. Okay. Well, let me just tell you what it's got. Do you see the little pencil that's moving around? That's okay. That's the draw part, and you don't see the draw thing. And that's where I do everything off the keypad, which is pretty pathetic. The text I could type in. However, there's no, I can't do a DP over DT without doing the slash. I can't do it the way we usually write the operator, D by D, D by D, okay? You can't do that. It doesn't have things like the proportionality symbol. It doesn't have a decent way to do superscripts or subscripts. Superscripts, you can do the caret key. Everybody sort of understands that. Subscripts, you just have to type whatever you're going to do next to it. So it's really limited in the text part. So basically, I'm left to the drawing part, and you'll see my drawing stinks, and I can hear you laughing already, and you haven't even seen it yet. Here was Malthus's model. I don't know if I'm pronouncing his name Malthus. I don't know. Population dynamics. D, that's supposed to be a D. P, that's your population, by dt, and by the way, the T is standing for time, okay? And you see this excruciatingly slow, okay? D by dt, dp by dt is proportional to, and that's a really pathetic looking proportional sign, is proportional to the population itself, okay? And if you think about it, that makes pretty good sense. The rate of growth of a population, or decline perhaps, is proportional to the population. The more people you've got, the more rapidly the population is going to grow. The smaller the population to begin with, it's going to start with a very slow growth rate. Okay? Basically, this is explaining or defining basically what you mean by exponential growth, right? Because what function, if you take d by dt of that function or d by dx of that function, you get the function. The exponential function. And if you think about the exponential function for very low values, small values, it's almost flat. And then it starts going up slowly at first and then takes off and goes. That's basically what happens with populations. For very small populations, the growth rate is very small. For larger populations, it increases fairly dramatically. Now, you can adjust the degree of increase by changing your the argument. You know, it's not just e to the x, it could be e to the 0.3x, e to the 0.001x. That's going to flatten the curve for a lot longer, but it's still going to be exponential growth. This was Malthus's model. I'm not even sure he knew exponential functions then. I assume he did, but this is his model for population growth. Now, I don't know if in science you've run into it before, but you can change a proportionality to be an equation by simply dp dt. I get a little better with time, but not much, and not always. You change the proportionality symbol to an equal sign by doing equal k, some proportionality constant, okay? and then that's multiplied by P. And that's his model. Now the K here, if the K is positive, that's exponential growth. If the K is large positive, it's really fast exponential growth. If K is a very small value, like 0.1, 0.01, something like that, then it's a very, very slow, but still exponential growth. If K is negative, on the other hand, exponential decay. And we'll talk about that coming up later, exponential decline, okay? Most populations are positive decay. Now, I think we're going to hit this a little bit later, but I'm going to go on and say it now. Any of you been following the virus? Whether you want to or not, you probably have. My wife is, oops, here comes Dawson. Okay, let me get a marked present. Okay, Dawson, we're already started on 1.3. Okay, right now, your first impressions. Would you rather go with whiteboard or me holding up a piece of paper in front of the camera? Whiteboard? Okay. Dawson wants to punish me for something. Okay. All right. We'll go with this. Okay. I was just asking the question. This is population, Malthus's population model, that the rate of change, and by the way, I should have said this to begin with. When you read a problem, when you are formulating a problem, like we did the hypothesis, okay, a rate of change is a derivative. D by dt, that's a time rate of change of whatever is up here, population, whatever. You're already probably familiar with it. Time rate of change of displacement is velocity. Time rate of change of velocity is acceleration. You're probably used to those. This is time rate of change. If something depends, the rate depends on something else, that's your differential equation. There's your derivative. Anytime you see the word rate or something changing with time, changing with anything, miles per gallon, that is a derivative. ds, if that's your distance, per dA, if that's the amount of gas, gallons. Whatever it is, if something is measured in a ratio like that, that is a derivative, can be used to represent that. Okay, now let's go back to the, I was going to say, my wife is an infectious disease epidemiologist. She's a professor at UAB. She actually studies other viruses, not this one, but she knows enough about it to be able to follow it and understand it. She says, especially here in Alabama, but I believe across the country too, our K here is not very large, but it's still greater than 1. Okay? And if that K is greater than 1, you've got exponential increase. Once we get that K to be less than 1, then we'll see the declines happening. But right now, or the last time she looked, and that was maybe a day or two ago, maybe over the weekend, she said, she doesn't call it K, she calls it something else. The rate is still greater than 1. It wasn't much greater than 1, but it still was, meaning we're still on the rise. Still on the rise. Now, you'll have fluctuation. You might drop below 1 one day and then go back the next, or 2 or 3 days. But overall, in some sort of, what do they call it, rolling average, we're still greater than 1. And that's exactly what we're dealing with here. Okay. Now, does this work unlimited? No, of course it doesn't. Okay. Because once a population reaches saturation on something, food supplies, housing availability, people being packed together so tightly, diseases are spread. Think the plagues of Europe, stuff like that. Yeah, this falls apart. But for small populations with no limitations on your other inputs, this is a pretty good model. Okay. Now, it works there. Here's another place it works. This is radioactive decay or radioactive. Well, yeah, we'll just use decay. Here's the formula. I said that it gets better. It doesn't always. dA dt, that's a D there, whether it looks like it or not. Yes. Okay, say that again. You have some sort of stylus and a something laptop. What did you say? Right. That's what that's what we used to have. Yes. I know you can do it a lot faster than this too. The thing is, can I give the screen control to you? Okay. Yeah, that's exactly your yeah. Oh, look at that. Okay. Do you have your book open? Okay. Do you see on page 23? Do you have a physical book or an ebook? Okay. Bottom half of 23, DADT is proportional to A. It's just like we did before, only with P's there. Or you could write that as DADT or D by DT of A is equal to KA. Okay. If you want to write that, you certainly can. It showed up. The D showed up here. Did everyone else see it? Or big red D? Okay. Do you want me to clear the screen so you have the whole screen to work on? Okay. Okay. Well, I'll clear it so you can, that way you won't be, people won't be comparing your nice writing with my ugly writing. Okay. Now you've got the whole screen to play with. Now, while you're writing that, if you want to, what is that saying? The amount of, and the A here is the number of nuclei, okay? The number of nuclei remaining at any time t is the rate at which that number is decreasing is dependent on the amount that you have. The ADT is proportional to A, which is another way of saying the ADT is equal to some K times A. Okay. You're doing much better than I. Okay. Now, um, this works in a positive sense. It works in a sort of negative sense too. Um, I had many years ago an angiomyolipoma, which angio means blood, I think. Myo means muscle. Lipoma is lipids, fat content, little fatty things. These were knots, growths. I got one on my arm here. It's just a little knot there. It's just angiomyolipoma. Okay, not dangerous, not harmful and stuff. The trouble is, it happened to be on a kidney, and this one was growing on the kidney. And they said it could rupture at any time, so they decided to take out the angiomyolipoma and leave as much kidney as they could. This was right kidney. That was a lot more major operation than it sounded like it was going to be. They could have done arthroscopic, no, that's not what you call it, whatever, the small incision and just suck the whole kidney out, but he wanted to leave as much kidney as possible. He thought he could leave half. It turned out being less than half, but because it had really infiltrated. But why am I telling this story? Well, afterwards, he wanted to see if that kidney that had been abused like this was still operating properly. So they injected me with radioactive magnesium, I think. I believe that's what it was. And so the amount of that radioactive magnesium, and it went away in a fairly quick time. I drank plenty of fluids and it flushed out. But for the time that they were doing the test, the amount of the and they could read, because it was radioactive, they could read something on the screen that would tell them, it was lighting up the screen and showing how much of it was going in one kidney, how much of the liquid that they had me drink was going in the other. They injected, I can't remember how they did it, but anyway, that was a very positive use of a radioactive decay. They were able to determine that second kidney, and it was fairly soon after the operation, was doing about 1/6 of the load, and the other kidney was doing 5/6. They were hoping for like a quarter and 3/4, but hopefully it's gotten better over time. But I haven't had another test. But that's what this is used to measure. They don't just use that. Iodine they use for some things. Tumor growth they can inject and see if a tumor is increasing, decreasing. Yeah, there's a lot of very positive things. Of course, nuclear bombs are used. The same principle. The rate at which the material is increasing or decreasing depends on how much material you have. And in a nuclear explosion, and actually, to be fair about it, nuclear reaction of any nature, if they can control the amount of that's being the interacting, you can control the reaction. And a nuclear bomb, they reach critical mass and then it explodes big time. And a nuclear reactor, they control that, keep the critical mass right at that level of being a critical mass. And they do that by using tubes that have heavy water, extra neutrons. The neutrons absorb some of the, I think it's gamma radiation that, or possibly alpha whatever the radiation is that is creating the reaction, they control it by that. So radioactivity, radioactive decay, same formula we use for Malthus's population model. Okay, here's another one. If you turn to page 24, it's called Newton's law of cooling or warming. Either way. And there is dt by dt. Now, if you've had physics, you're probably aware of this. Capital T represents temperature in physics. Little t represents time. So this is d by dt of t. Okay, but it's different t's. The time rate of change of your temperature is proportional to the difference in temperature between the object and the ambient temperature. They use T sub m, which is the temperature of the surrounding medium. Okay, I'm used to calling it ambient, they call it surrounding medium. Same deal. Okay, so if you have something that's very much hotter than the surrounding environment, it's going to cool much more quickly. And that makes sense. Okay, however, if it's very close to the ambient temperature, it's going to cool a lot more slowly. Okay, and sure enough, this is it. And as if he didn't have enough to do, coming up with the three laws of motion would revolutionize physics, developing a whole new branch of mathematics called calculus, from which we get differential equations, or discovering stuff about gravity, light, and everything else. Newton also came up with this rule for temperature. D by dt is proportional to the difference in temperature between the object, and the rate at which an object gains or loses temperature is proportional to the difference between the temperature of the object and the ambient temperature. Now, of course, that K that she just wrote down is going to be positive if the, let me see if I'm saying this right. I believe it is. No, probably negative. Whatever. If the capital T is greater than if the object is hotter than the surrounding air, then the rate of change is going to be a cooling. So that would be a negative K. However, if you pull something out of the freezer and you're letting it thaw in the sink or something, then your object's temperature, the T here, is going to be less than the ambient temperature. So now it's going to warm. So then you're, let's see, no, yeah, you use the same K. You do. If that's a negative K, this would then be a negative temperature, a negative difference here, because your temperature here is cooler than the ambient. So that would be minus. So that means the d by dt of t, your temperature, is still, in this case, is increasing. So it's the same k. Okay. I haven't talked through that, but it's definitely true. It stands to reason that k has to be less than 0. And sure enough, it is. Okay. Now, bottom part of page 24, spread of a disease. Now, unfortunately, folks, there's not a lot of differential. I mean, we're using differential. We're showing how differential equations are used. But notice here, we're talking about rate of change of amount, rate of change of temperature. Anytime you have a rate of change, that's the d by dt. Here we have spread of a disease, a contagious disease, like the flu or COVID virus, okay, a coronavirus. And this one is written, do you need me to erase the screen or do you want to keep writing? Okay, okay. The x is the number of, let's see, it seems reasonable to assume that the rate, the x dt, at which the disease spread. Okay, here, okay, had to find. Let x denote the number of people who have contracted the disease. Now, right now for COVID, that's a pretty small number, relatively speaking. I think we're still probably 1% or less. Okay. Number of people who have contracted the disease. Y denote the number of people who have not yet been exposed. Then it seems reasonable that the rate of exposure, dx dt, of the rate of people who are going to catch the disease, at which the disease spread, is proportional to the number of encounters or interactions between the two groups of people. And that's why dx dt is equal to, you could have said proportional, but they start right out with the equal. Why go with it? To k times xy. Now notice, right now, x is small, okay? Y is pretty large, okay? So the rate is relatively low right now, okay? Now, what do y'all think about masks? Like them or don't? Anybody? Yeah, yeah, don't like to wear them, but you know, they are essential. Now, if you think about it, why do we wear masks? And you might think right off the top, it protects you from breathing in nuclei, uh, saliva nuclei, is that the good way of saying, or mucus nuclei, or whatever you want to think of, that someone who may have recently sneezed or something else from breathing that in. Actually, it does do some good that way. It blocks some things from getting in. But it's even better, it's blocking your nuclei from reaching them. You may be asymptomatic. You may actually be emitting viral parts that people could actually catch it from. Actually, the mask is more to protect others than it's to protect yourself. It does have some self-protection, but it's more of protecting somebody else. Okay. And so what you're doing there is changing the K. It's changing the rate at which you're being exposed. Okay. Social distancing, again, decreases the K. Okay. I think the app that Apple and Google are working on now, and it's pretty close to coming into fruition, I think. And Alabama, believe it or not, is one of the 3 or 4 test states they're going to try this app on. Okay. It's going to, just using Bluetooth, I believe it is, from cell phones, it's going to identify anytime you're within, I believe it's 6 feet for more than 15 minutes of another person. Now, it's not going to identify the person. It's not going to identify where this is happening. It just identifies if you're within 6 feet of another Bluetooth cell phone smartphone for 15 minutes or more, and then that other one, sometime in the next 2 weeks, they self-report that they have symptoms of the disease, you will be notified that so many days ago you were potentially exposed to someone who is now either tested positively or has symptoms or whatever. It's not going to say who it was. It's not going to say where it was. I don't even know if for sure if it says when it was, just something within the last so many days. So you really don't know who it was or where it was, but you know there was a chance. Then that means that you may have grounds for being tested. Okay. And and that way they're going to get a better handle on tracing. And that's the thing we don't have any piece of this puzzle, at least I know of, that's in play right now. My wife says that Alabama is actually one of the best states in the nation for tracing tuberculosis because I guess, being a rural southern, lots of mosquito or whatever, the environment is right for tuberculosis transmission. And we don't have many cases, and one of the reasons is they have a great tracing mechanism in place. And it can work when there's not many cases. It's really easy to do tracing. With this stuff, and, and it's just a free for all out there right now. People not wearing masks, wearing masks. No one's keeping up with anything. They're not. I think the Chinese did a totalitarianly good job of doing tracing within that Wuhan province or whatever, and they got it under control rather quickly. They did really strict quarantine and stuff like that. The South Koreans have done a great job. Singapore has done a great job. Czech Republic did a fantastic job. I don't know if they had the tracing in place, but they did what it took to keep that K right there small. Okay. And that's the thing we haven't done. We have done nothing about the K. And part of the reason, unfortunately, is we seem to have the people who are calling the shots either they don't understand science, which I think is very true, or they don't trust science, which unfortunately seems like it's true. And it's just sort of seat of the pants type stuff. Not the way to go. Okay. Sorry, I'm on a soapbox there. Now, her second formula she wrote down here comes from the fact that now they introduced a new variable here, and this n is a fixed population of n people. So if you have a fixed population of n people, and x is the number of people who have the disease, then n minus x would be the number of people who don't have the disease, right? But you introduce one more person into the picture who has the disease. You have to have someone bring it in. So that's where the +1 comes from. Rather strange. It took me a long time to figure out why in the world they have the +1 in there, but that's why. Okay. And this is then the way you eliminate the y variable because you know the formula x plus y is equal to n plus 1. So you can eliminate the y, and that gives you the new formula. Y is equal to n plus 1 minus x. So that's where this one comes from. Now, sorry, do I have 4 people? Yeah, I have 4 people here. Okay, now, Melissa, do you know what I think it's called the sigmoid curve looks like? No, well, I think I can do this. It's all right for me to clear the screen, and I'll do a very lousy rendition of what a sigmoid curve looks like. Okay, a sigmoid curve, and I think I'm saying it right, and this is not, it's not supposed to be jagged like this. It's very slow increasing at first, then it increases extremely rapidly with no gaps in there. I don't know why the gap showed up. And then at some point starts decreasing and levels off. Basically, this is a typical disease curve. These could be flatter, they could be sharper, they could be greater curvature, lesser curvature, a variety of ways of doing it. What happens down here, very few people have the disease. It's a lot like your population growth. Very few people have the disease, but the more that get it, then the more they're exposing others. Okay? And then at some point, you reach an incredibly rapid increase in disease. At some point, though, you begin getting to saturation, and most people have had it, so now the rate of increase levels off. This is approaching your population up here, total population. Okay? Have y'all heard the term herd immunity? That is somewhere around in here, I think around 60%. I don't know exactly where that is on the curve, but something like 60, 65, 78, some percentage there. You get enough people have the disease that your rate of increase declines. We want to get there, but we don't want to get there through this means. Because what this means right here, you're going to saturate your emergency room. You're going to saturate your ICUs. You're going to saturate the number of ventilators and stuff. This happened in New York. I believe it happened or came close to happening in Montgomery. Their rate of increase spiked so quickly, they didn't have enough hospital ICU beds to accommodate the patients. So what does a K do for you? If you can decrease the K, that flattens this curve and it takes a lot longer for it to reach saturation. So what does that mean? If you don't control the disease, you're going to have incredibly fast increase in the disease. And that, especially with this disease, it causes so much issue. I don't know if you caught the story. There was a policeman, UAB police uh, person, came down with it. He was hospitalized, I think, for something on the neighborhood of 6 weeks in ICU. And I believe something like 3 of those weeks were in with a ventilator. And usually, most people, if they're on a ventilator that long, the only question is when do you turn off the machine and let them die, because usually they don't survive it. He was a big, strong policeman and probably in pretty decent health. He recovered, even though being on a ventilator that long. And so you don't want that happening. You don't want the K to be this big. And that's why the masks, the social distancing and stuff, is probably not going to change the fact that we're all probably going to wind up getting the disease. Or if they come out with a vaccine, that we can get the antibodies to keep from getting the disease. But that vaccine is going to be way down the road here, a year and a half, 2 years, probably at the least. So what we're doing now is trying to keep the K small to slow to the rise of it. And believe it or not, the Czech Republic is back in business because they have controlled the rate. And sure, they have flare-ups, people are still getting it, but they can do their tracing, they identify this, they put quarantines in place, they sort of stop it in its tracks when they do have flare-ups. And that's what we need to be doing. That is not what we're doing. We're trying to do it with what we can with social distancing and mask wearing and stuff. And cities are trying this and others, but still, we're Americans and we don't like to be told what to do. So not everybody's doing it. We need to avoid this. We're still down here. We can do things now that will keep K from getting this steep. But if it gets this steep, hey, the economy is going to shut down. I mean, because you have so many sick people, our health system's going to get very unstable. All sorts of bad things can happen. That's the reason you try to get the K to be as small as possible so you can to do. And literally, you can actually almost stop the disease in its tracks, keep it from getting on the rise here by doing enough of this. And sure enough, it will slowly, slowly, slowly probably keep going. But guess what? And here's what my wife said: if we're all going to get it, I'd rather get it next year, okay? Not this year, because they still don't know for sure what the best therapy is for this, what the best. They're developing right now across the country and across the world, probably hundreds of drugs are under trials to see if they are effective against this. Not vaccines, drugs to um, treat the disease. I don't know if I've told this class yet or not, but I have a mild form of leukemia. Okay. It was discovered in 1991. So when I said mild, it's mild. Okay. Y'all probably weren't born in 1991. I'm approaching my 30th year with this disease. And as the nurse said not long ago, it's right now not curable, but it is treatable. Okay. I just had a blood test last Friday, got the results over the weekend. I have a consultation with my doctor, teledoc type thing, telemedicine, this afternoon. He'll decide whether I need to go in for another treatment. Right now, taking 1, 2, maybe 3 treatments a year, it knocks it back and controls it. It's treatable, not curable, but treatable. That's what we're wanting to find. We want them to come up with the drugs while we're down here somewhere, stretching this curve out somewhere so that when we finally, if we do catch it, we want to be after they got good treatments, they got good protocols, they've got good practices that they can do. They're doing, UAB Hospital is doing a superb job. I'm sure they've had some deaths, but they've been able to maintain their ventilator, the ICU on ventilators, right around 60%. They haven't gone. They've been able to get people out before the next people group comes in, and not group. It's a continuous thing. So we're developing good things now. We want to wait until after they're developed and we got good treatment. Maybe even if we can last until there's a vaccine, even better. Okay. But right now, you don't want this to occur. All right. That was way more than you paid for, wasn't it? Okay. Uh-oh. Somebody's coming in, but I can't say. Oh, Ricky's here. Good deal. So Ricky is coming in pretty soon. Hopefully we'll be here soon. Now we're only missing Billy. Where in the world is Billy? All right. Ricky, are you in yet? Okay. We're in chapter 1, Introduction to Differential Equations. We're in 1.3. I'm talking way too much. We're on page 24, bottom part of page 24 if you have a book. We just finished talking about spread of the disease, and that wasn't a very timely subject at all, was it? Okay. Uh, all right. Let's move on to chemical reactions. So I'll clear the screen here so Melissa can write again neatly. Okay. And you don't have to write all, well, if you want to, you can write them down. It's up to you. Okay. Here's 2 equations here. Uh, and they talk about a first order reaction, a disintegration of a radioactive substance governed by the differential equation is said to be a first order reaction. That's the one we did a couple times examples ago. In chemistry, few reactions follow that same empirical law, because in a chemical reaction, you're not destroying anything. Nothing is being destroyed. You're just moving atoms and compound, or basically atoms around. Okay. So if the molecules of a substance A decompose into smaller molecules, it's a natural assumption that the rate at which the decomposition takes place is proportional to the amount of the first substance. So that would be pretty much our dx dt. Okay, yeah, she's writing down the formula here. Um, that is just the decomposition. That would be like nuclear reaction. Okay. But a lot of times, an example of a first order chemical reaction is the conversion that she's writing down there. The first of those is called um, T, see, T-butyl chloride, okay? And that's what she's writing now. That's her, this is, it's actually more of a methyl thing. I don't know why they're calling it a butyl, because, no, I'm sorry. It's CH3 of them, okay? You have, I think you left out C right here, okay? You have, yeah, good. There is a C. Now, carbon has, um, John Dalton called it hooks. We know it's not hooks. Carbon has 4 unpaired electrons in its outer shell, and it loves to pair those things up. So it pairs one of these, 3 of these up with a methyl group, okay? And that's the part I'm not understanding why methyl isn't in here somewhere. Methane is CH4. Take away one of the H's, you leave that carbon here in this radical with, it has 4 unpaired electrons. 3 of them are paired with the hydrogens around it, okay? The 4th one, though, ties in with this carbon here. This carbon has 4 unpaired electrons, so it has 3 of these methyl groups tied to those three of those unpaired electrons. The 4th one is connected to the chloride, okay? So a carbon wants 4 things around it. It has 3 methyls and 1 chloride, okay? Combine that with sodium hydroxide, NaOH, sodium hydroxide, and you get, I think it's T-butyl alcohol, okay? Now, again, you need another C right here. Yeah. Right. Yeah, you're looking at the one below it. Sorry about that. I see now. I see now what you're doing. Okay. Yeah. So this, all you've done here is exchange the chloride here with this OH from here. So that forms your T-butyl alcohol, which that's what this is, and sodium chloride. Okay. So you see the chlorine went from being with the T-butyl chloride to the T-butyl alcohol, and the chloride that left here joins with the sodium from here and forms sodium chloride, salt, okay? So now you have a salty solution of T-butyl alcohol, okay? So that is mostly a first order reaction. You're decreasing the concentration of this and increasing the concentration of this, okay? Uh, that's a C and an OH, okay. Now, in the second formula here, the T-butyl chloride, no, I'm sorry, this is now methyl chloride. That's what this is, methyl chloride. And this is a methyl group. This carbon has 4 potential sites, 4 unpaired electrons. 3 of them are taken up by hydrogens. If the 4th one was, that would be methane, okay? But the 4th one now is a chloride. So they call that methyl chloride, okay? It's not methane, but methyl chloride. You combine that with sodium hydroxide, just like here, and now you get, and the title of this one is methyl alcohol, okay? And not T-butyl alcohol, but methyl alcohol and sodium chloride, okay? Now it looks like this would be very similar to that one, okay? In fact, I don't see any big difference in them at all. Your concentration of this depends on this. But they say that 1 molecule of sodium hydroxide is consumed for every molecule of methyl chloride. Same thing was up here, so I don't see why they're making the distinction there. But anyway, that leads to, and this isn't a chemistry class, so we're not going to the time rate of change of your concentration of X, where X is whatever the chemical you're looking at. T-butyl chloride, uh, methyl chloride, whatever it is, the time rate of change that's happening is equal to that proportionality constant, then times the that's an alpha minus X times the beta minus X. The alpha represents I think, the concentration. Um, yeah, I can't see it. I know it's here in the book somewhere, but this really isn't written very well. Definitely not a chemistry book. Um, Alpha and beta are in turn the amounts of the two chemicals A and B. Okay, where X is the thing that you're changing, and the A and B, I think, is the sodium hydroxide and the sodium chloride. Okay, yep. So that would then be, and they call this a second order reaction. So the rate of change is not just dependent on the change of one variable, but the change of two variables. So it's called the second order reaction. Now that's a lot tougher, well, somewhat tougher of a differential equation to solve, but it's still solvable, okay? And we don't know how to solve them yet. Again, this chapter is just introducing you to the whole. Now, I bet you from back in an algebra class somewhere, you loved your mixture problems, didn't you? Okay, you remember those fondly? What you have with a mixture problem is something coming in, and the picture they give in the book, and since my picture's still up here, I will show you if you don't have a book. It should bring back fond memories of an earlier algebra course. You have something coming into a solution, that's your input, and being mixed thoroughly, and then you have an outflow. And the stuff that was in the container to begin with had a certain concentration. The stuff coming in had a different concentration. And the question is, what is the concentration of the stuff coming out? Now, that's not worded in good technical terms, stuff, but you get the general idea. Okay? So, the stuff in this problem is your A, the amount of, and let's say it's salt. Okay? And in fact, in this problem, they're going to say, let's suppose that a large mixing tank initially holding 300 gallons of brine, that is water with a certain number of pounds of salt dissolved. Uh, Karen fixed some really good barbecue chicken over the weekend. She took the chicken breast and put them in brine before she barbecued them, and they came out so juicy and good. I'm hungry right now. Okay. So anyway, um, there's a certain brine solution in the tank. Another concentration of the salt in the inflow, let's just say, and you're given a rate of inflow 3 gallons per minute, there is a derivative, gallons per minute. Okay? Anytime you see a per, you know that represents a derivative. So the brine solution is pumped in at a rate of 3 gallons per minute. The concentration of the salt of the inflow, 2 pounds per gallon. Another differential, a derivative, 2 pounds per gallon. When the solution in the tank is well stirred, it is pumped out at the same rate as the entering solution, so you maintain that 300 gallons in the tank as a constant, but now the outflow solution is, uh, you know, a different concentration of what the inflow was, because the inflow was different from what was in the tank. So that gives us the formula she wrote at the bottom here. The change in salt, A is the amount of salt in the solution per unit time, is the input rate of salt minus the output rate of salt. And that's what she's typed in. Oh, look at that. She's done such a good job with that. Input rate of salt minus the output rate of salt. She's working on that one now. And that's equal to Rn minus R out. So the input rate of salt, now that's a rate, remember, a derivative, 2 pounds per gallon. The input rate of brine was 2 gallons per minute. So the amount of salt coming in was, notice, and I don't want to write them down because she's doing such a good job. Um, but you see the formulas there that you're dealing with. I think I'm on the right place because I'm looking at it backwards. No, I was up, down too far. Yeah. Okay. I'm still, oh, there it is. Okay. I think. Yeah. R sub n. Get closer. Yeah, now I can see it better. 2 gallons per, I can't read it. 2 pounds per gallon and gallons per minute. Okay. You see that equation there? 2 pounds per gallon times 3 gallons per minute. Notice units are your friends. Keep up with them. The gallons cancel out because one's pounds per gallon, the other gallons per minute, and you're left with units of pounds of salt per minute. That's your rate of salt. Okay. That is the input rate of the salt. If you know the concentration coming in, then you've got that point. Okay. You're probably looking for the concentration going out. Okay. And that's going to be the amount of salt per 300 gallons, because that's what's in the middle there. If I can show it. Okay. Um, and your unknown there is what the concentration is going out. That's your A of T. But you know you're going out at the same rate you were coming in. So that gives you a differential equation there. And then the sum of those, or the difference in those two, like you saw she wrote above there, is then the time rate of change of your output rate of the salt. Okay. So it's a little convoluted, but it's all there. Okay. So they rearranged the order some. The output rate, our input rate of salt was 6 pounds per minute. The output rate of salt is A divided by 100, the amount of salt in there divided by 100. The ADT is in that. So, Melissa, you want me to erase the top part here? Okay, let me hit that. See if my eraser will work with yours. Yeah, look at that. Oh, I get to destroy. She creates, I destroy. Destroying is much easier. It's kind of tedious writing, isn't it, Melissa? Oh, yeah. Yeah, you're having to cross your eyes or whatever, you know. Okay. But you do have the stylus or whatever you call the ionizing pen. Okay, that sure makes it a lot easier. I don't know if I can erase below the window. Yeah, okay. Hopefully that gives you enough to work with. Okay. Nope. Oh, I'm in trouble now. I don't know why this does it, but after a while it won't change. Now I've got an eraser permanently. It won't go back to a drawing again. Yeah. So you draw, I'll erase. Okay. Um, but anyway, after all that work, you come up with, and there's a couple of differential equations you're fiddling with there, but you put them together, and the ADT is equal to 6 minus A over 100, and then you can rewrite that as the ADT plus 1 over 100 times A is equal to 6. Now you might say, why in the world would they change it to that form? Well, coming up in the next chapter, we will actually start solving some differential equations, believe it or not. Not immediately, but after a while. And that is what we call a linear equation in the standard form for a linear equation. And that has a very special technique to solve that equation. Okay. So that's why they rewrote this one slightly differently from what they did the earlier ones. Okay, so uh, that's all you have to do on that one, Melissa. All right. Now, draining a tank. That may have been another one of your favorite problems in a former algebra class, Torricelli's law. Now, since he's mentioned in the book, hey, guess what? You can write. We already mentioned Newton. You could write on him. Torricelli, you could write on him. Torricelli's law. How did he come up with it? Who uses it? Whatever. This doesn't have inflow. It does have outflow. And you're not dealing with concentrations because whatever is in the tank is leaving the tank. It has a formula, and she's writing it now. The change of volume per unit time, that's a derivative, dV dt, is equal to minus some. Now, this time they identified, I think, I've got to find where they mentioned it. Oh, no, that's not a constant. Well, it probably is. Okay. The area of the hole is A sub H. Okay. Um, that's once you have the hole there, it becomes a constant. Okay. And the rate of change of the volume of the tank is uh, equal to the minus the that. Now, why is it a minus sign? Well, the tank is obviously losing water, so the rate at which it's losing water has to be a negative rate. Okay, so therefore, and the A is the area of the hole down there. All right, now what is that rate? Well, that goes to um, the change in potential energy of the water in the tank, uh, and that's changing according to the height, and the height is depending on the, and here they say V, that's usually velocity. Yeah, it has to be velocity. And this is from your conservation of energy, basically, that 1/2 mv squared is equal to mgh, where the kinetic energy coming out equals the potential energy at the top. Um, and so you solve that for V, the M disappears because it's on both sides, and you have V is equal to the square root of 2gh, where g is the acceleration due to gravity, h is the maximum height of the tank. No, I'm sorry, it's probably the height of the water in the tank. So your dV dt, no, it's the height of the tank, I think, okay, is equal to that. And she's already written that down. Now, to get that, that is the rate of change of the volume, but you have the rate of change of the height, and that's what our second equation here, that's what you're more interested in. How rapidly is the water going down? That comes to be minus the A sub H divided by the A sub W. What's the A sub W? That's the area of the tank. If this is a cylindrical tank, that's the cross-sectional area of the tank. So don't worry, you're not having to come up with the physics or the reason for this. What you're dealing with is what to do with these equations once you get them. Again, we haven't solved any of these yet, but here's a differential equation. The variable here is the height of the water in the tank. How rapidly is that going down? It depends on the area of the hole, the area of the tank, and here is where the H occurs. Now, I think if I were to ask you, is this a linear equation? Ooh, anyone remember what was meant by a linear equation? Your dependent variable H here that shows up in the top part of the d by d, that's the H. Over here, that's not a linear relationship. 2 and g are constants. Don't worry about them. But the H is the variable. That's not linear because you have a square root of that H. Okay, square root of 2g is just a number. Okay, it's a constant. but the square root of h is not. So this is not a linear equation, so they didn't wind up writing it in the same way they did the last one. Okay. All right. I think she's already gone down to um, series circuits. And this is actually an LRC's series circuit. Any of you in either have already completed your electromagnetic part of physics or are you in it now? I think Dawson's in it now, aren't you? Or did you finish it? Okay. You finished it, okay. Did y'all do LRC circuits? Those are circuits with inductors, resistors, and capacitors in them. You may have just touched on them, I don't know. But that's what we've got here, and I'll show you the picture of it here. Okay. Here is your voltage supply. Okay. And by the way, that is a alternating circuit. That is a generator. This is not a battery. Your inductors and capacitors do not work with direct current, only with alternating current. Here is your inductor. That's a coil of some nature. There's your resistor. There's always some sort of resistance in the wire, but you probably have a resistor there. And here's your capacitor. Capacitor is two parallel plates that basically store charge. But because this is alternating current, the inductor, a coil of wire, now I hope you remember this from somewhere in physics, that anytime you have a moving charge, you induce a magnetic field. And when you have a coil of wire, you have a much stronger magnetic field because of the winding of the coil. Okay, so that is producing an alternating current there is producing a magnetic field, a changing magnetic field in your inductor. But a changing magnetic field creates an impedance, which is like a resistance, but not quite the same. Okay, so that is decreasing the effect of your alternating voltage that you have in your system. The R just acts like a resistor. I mean, it's a linear type thing. The capacitor, though, however, it's a parallel plate that builds up charge. So when the alternating current is going one way, you're building up charge on this plate, depleting charge on this plate. But then when it changes its direction, they start moving in the other way. So that creates another impedance, and that's a capacitive, you might say, impedance or resistance. Okay, whereas the R is just a resistance, and then the L is an inductive impedance. Something impeding what? Now here they mention Kirchhoff's second law, and if you remember that one, that's called the loop law, and that says that the voltage that's supplied at one end has to equal, that's the voltage increase supplied, is the voltage drop across each of these elements. Well, the voltage drop across an inductor is different from that of a resistor, and that's different from that of a capacitor. And I think she's written down, Melissa has written down the formulas here. This is L di dt, and sorry if something keeps popping up there. That's your inductor times the change in current per unit time, okay? And change in current, if you remember that from physics, current is change of charge per unit time. I is equal to dq dt. So this is a d2q dt squared. That's what your inductor is. Your resistor is I times R, but I is dq dt, so this is R times dq dt. Well, a capacitor is building up charge, and that's why we went down to charges, because one of your of the capacitance times the charge is the amount of voltage drop across the capacitor. Okay, so if you put these three together, the voltage drop across a inductor is L d2q dt squared plus R times dq dt plus 1 over C times Q. That's going to be your voltage drop, and that's going to have to equal the E of T, okay? And that's the formula they show. I can't tell if Melissa has it because all these names are in the way, and Melissa, you're one of them. Let me see if I can move this out of the way up here. Yeah, there we go. There's the formula. Now, by the way, what order differential equation is this? Second order, linear or nonlinear? Linear, because L is just a constant, R is just a constant, 1 over C is just a constant. Doesn't matter what this thing is over here, though we know it's a sinusoidal curve usually. So yeah, this is linear in Q. You have a second derivative of Q here, first derivative of Q there, no Q's over here. That's a linear second order ordinary differential equation. Okay? Quite solvable. Looks ugly, but it's quite solvable. These are just constants. L, R, and 1 over C are just constants. Okay. So, falling bodies, Isaac Newton took this from, do you want me to erase the screen? Okay, I've got to move. Dawson, of course, is in the way again. Okay, so let me clear the screen. Let's see if it'll clear. Yeah, it did. Still got only the eraser to hold on to, but I've cleared it. All right, so here we have falling bodies. This is Newton's first law of motion. Okay, it's the law of inertia. Actually, he took it from good old Galileo. Okay, um, that was famous rock off the Leaning Tower of Pisa. I think it's documented that true enough, Galileo probably did go to the top of it. He lived in Pisa. Why wouldn't he have used his power there to drop the rock and do the measurement stuff? And this is how he came up with the first law. He didn't call it that. Later, Newton refined that law and called it the first law of motion. He gave Galileo credit, but that was it. Now, the second law of motion is that the net force acting on a body is its mass times its acceleration. Okay, so basically combining, well, in a sense, combining those two, and that's what Melissa's writing now. You come up with d second derivative of displacement with respect to time. That's acceleration. So mass times second derivative of displacement with respect to time is equal to minus mg. Well, that's the rate at which it falls. I mean, this is your acceleration is the acceleration due to gravity. And that's what she's writing now. The d2s dt d squared is minus g. And from this, then if you know your initial displacement and your initial velocity, then you come up with the law of motion. Okay, and that's what she's writing now. Actually, there's quite a bit to write. I'll hold up the picture. I'll see if I can get the picture to hold up. Okay. She's doing that part. The equation at the very bottom of that paragraph is what we're going to get. And you're pretty familiar with it, I think, especially if you've had physics, that your position at any time t when you solve the equation she's working now, which is a second order linear differential equation with two initial conditions. Okay, and that's a prime there on that second s. If you know the initial velocity, then this is the equation you get. S of t is equal to 1/2 negative 1/2 g t squared plus v0 t plus s0, where v0 t is initial velocity, s0 is initial displacement, and that gives you your rate, that gives you your position at any time t. Okay, that's your solution to this differential equation. Now, we're not there yet, but you probably recognize that from physics. Okay, and we will, whether we actually do that one or not is so common, we may not actually do that one. That's what we've got here. Okay, and she's writing that equation here, the one I was just showing. So another example. In fact, I mean, we're almost going full circle here. Newton developed calculus so he could describe motion. Now, he was mostly interested at that time in planetary motion because Kepler, I think, had come to him with a problem saying, look, I found out the equations that make planetary motion make sense. I just don't know why they work. Can you give me a theoretical basis for why they work? Well, Newton tried and tried and tried and had to come up with calculus to give him those formulas. And sure enough, he did. And this is one of those that came out of that. So we've gone full circle. Newton came up with this technique of calculus, which differential equations derive from, in order to solve problems such as this. And now we go backwards in time. I mentioned the first law of Newton's first law of motion actually came before um, Newton, and that was Galileo on the Leaning Tower of Pisa, which I showed just a little bit ago. But he also dealt with air resistance. Galileo was interested in falling bodies, as in the rock off the Tower of Pisa, but he also realized that there was a slowdown, especially if one of two things was happening. If the velocity got too large, that slowed things down, or if the medium through which the object was falling was too viscous. So in other words, you drop a rock from the top of the second story of your house, it's going to fall following this formula that Newton came up with right there. Okay? However, if you dropped a rock through an equal height of water, you had a tank of water that was 2 stories high, dropped it through there, it would not fall at the same rate. Why? The water is more viscous than the air. Air has very low viscosity. It has some, but at that short height, you don't notice it much. Water, definitely. If you had a tank of molasses, boy, it's going to take a long time for that rock to fall through it. Okay? Honey, whatever you want to use, oil, whatever. Some may remember the old Prel. No, you won't. You're too young. Prel was a shampoo that came up, but it was so rich. A pearl dropped through it, went through so slowly. It's just saying it's a very viscous substance. Okay, they don't even make it anymore. And that principle now, you want to go and write at the bottom, or you want me to erase? Okay, let me erase. I meant to do it before you started writing, and then it's popped up there. You already got it. Okay, we come up with the viscous damping. Okay. Now the left side is the same as we had before. Mass times acceleration, but acceleration is also written as dv dt, change of derivative for change of time. A derivative right there is equal to the force downward, which is mg, minus the resistive force, kv, and the k is your viscosity constant, I guess it's called. The the kV minus kV is viscous damping, and I think that k is called the constant viscosity or whatever. Maybe just called the viscosity. I don't know. And so that gives you another differential equation, which she is writing down now. And if you wanted to write in terms of displacement, then the dv dt is d2s dt because v is equal to ds dt. So that's the second derivative there. And your v is again ds dt. So now you could write the whole equation in terms of not your dependent variable not being velocity, but being displacement. And that might actually be much easier to work with because it's easy to measure initial displacement. Sometimes a little harder to measure initial velocity. So therefore, this formula is usually an easier one to work with. And she's almost through writing it right now. Another linear second order differential equation. The one up here actually is a linear first order differential equation. In V rather than S, or displacement, this is in velocity, this is in displacement. And in the displacement, it's a second order linear differential equation. All right. Now, good deal. That's the end of that one. Want me to erase? Say again? Okay, you got enough. Okay. The last example they do here is one of suspended cables. Okay. Um, and this, I'm thinking it was a Bernoulli that came up with that, but they don't ever mention his name here. So it may not have been him, but I know he did a lot of work with it. This is the same principle you use on suspension bridges that you see at the top there, but it's the same principle that accounts for the sag in a telephone, in a power line. Okay, you always have to have a sag. Why? Because everything has mass and gravity pulls mass downward. Okay, so the two formulas you have the tension. What she's doing, she's giving you the formulas there that you get from this illustration here. If you have a suspended cable, you have one force of tension pulling up one direction and another tension pulling in the other direction. And those are the T1 and T2 that you have here. Now, I'll keep this up there while she's doing that. You can see some of the relationship there between the two. The T1 is the horizontal tension at the bottom, and T2 is the angular tension, I think, at the somewhere up the curve there. Now, while she's doing this, I'll give you an illustration. Well, I've already told you why they have to sag, because gravity is pulling them down. They're going to sag. Even if you tension them as tight as you cannot get all the sag out. You can't. You can't possibly do it. If you did, you'd break your power pole. Honestly, okay? In fact, this has happened before. Hopefully, it will never happen to you. And I'm going to make this up because I can't swear this actually event happened. But let's say someone was stretching power line between poles, taking service to a new community or something like this, and it was the hottest part of summer when they did it. But they were trying to conserve on the line they used, so they pulled those as tense as they could. Couldn't get all the sag out, but they did it just as tense as they could get it. Okay, and if they did that, if they truly did that on one of the hottest days of the year, then when it got cold, you know what you do? It broke the power line, the power pole, or snapped the line, one or the other. I think the pole would go first. Okay. It literally will break a pole. If you do not allow that catenary in there, then when the wire, when it gets colder, it contracts, the length changes ever so slightly. But if it's as tense as you can make it here in the summertime, in the wintertime, that's going to pull enough to break the power line. Okay? I mean, power pole. Okay? Believe it or not, that has happened before. Um, And this isn't the same deal, but it did happen. Let me make sure. Let's see. We go until, remind me, 10:45. Is that right? Yeah. Okay. So don't let me go over. I got another class at 11. Okay. This is not the same formula that she's doing here, but this is that contraction and expansion. If you were laying railroad lines like they did back when they were building the Transcontinental Railroad, or anybody building a railroad line, they always have to leave a gap between the those long, however long those rails are that they're laying there. They've got to leave a gap between them. That's an expansion gap. If they were laying those in the wintertime, the coldest part of the year, and put them too close together, didn't allow enough gap in the summertime, that, believe it or not, that heavy duty steel rail line is going to warp. And then you have a derailment. And that does happen, okay? If they don't allow enough of an expansion joint there, okay? Same type deal with the power lines. And I'm not going into gory detail here, but there is your formula, dy dx. So simple after all that explanation here is equal to W, which I believe is the magnitude of your, goodness, where in the world is W? Oh, weight. That's the weight. Okay. The magnitude of the weight, which, okay. And then your T1, which is your tension in the horizontal direction. That's how much they pull on that line, stringing them between the poles. Uh, you're going to have that catenary, that dip in the middle, no matter how hard you try to stretch that wire. Okay. Now, here's the deal. What are we going to be doing? What lies ahead here? This is bottom half of the page. And Melissa, thank you so much. I think you're through writing for at least a moment here. What you're going to come up with is differential equations. That's what the book is about. Okay. What we're going to be focusing on is an analytical approach. Is there some way analytically that we can solve these differential equations? Okay. Now, once we do that, we may get what looks like a solution, but then there's these questions. Well, before we even get there, does that differential equation actually have a solution? If it does exist and satisfy some initial condition, some fixed value that you know is true, is it the only solution? Are there more possible solutions? What are some of the properties of the unknown solutions? What can we say about the geometry of the solution curves? Those are all questions. That's sort of a qualitative approach. Those are qualitative questions. We really don't know for certain if we have the answer or all the answers. Okay. However, now this is the sad part. We're going to spend all term trying to solve differential equations. And then toward the end, probably before we even get there, I'll tell you, most differential equations that you'll probably run into in real life are not solvable. Okay. And we can approximate them with differential equations that are, those are your models that we were just talking about. But what they're doing more and more, but still differential equation texts are not written this way, you do numerical analysis. You do there's a couple of different ways these are. Some are called finite difference formulas, some are called finite, I don't know, there's just a couple different names for them. Generally, what we're doing more and more is letting the computers come up with numerical solutions. Again, they're not exact, but you can get them to within whatever degree of precision you think you can live with. And that's numerical solutions. We're going to spend precious little time on numerical solutions. We're going to spend all of our time on analytical solutions, but in real life, you'll probably be doing mostly, you'll use some package that somebody else has already developed, and you'll just feed in the input and hopefully get out correct output. Okay. Um, and they sort of show that you have analytical solutions, you have qualitative solutions, and then you have numerical solutions. That's the Einstein figure at the top of page 29. Not really Einstein, I'm sure, but they like to represent any scientist as if he was an Einstein. You actually work them out. That's what we're going to be doing. We'll also do sort of qualitative stuff and maybe just a tad of numerical. But you'll find plenty of that. Now, remarks at the end of this, I usually don't want to spend too much time with it. In more precise terms, they say a dynamical system, which is what differential equations are representing. Why Newton developed it. It was a changing system. Dynamical system consists of time-dependent variables. So this is the time is your independent variable. And those are your state variables. Okay. Velocities, acceleration. The state of the system at any time is basically initial condition. The response of the system, that would be the solution. What's on the other end? In Kirchhoff's law, that was your E function. That was your voltage supply. Now, you have a bunch of problems here. We didn't do any of these, but you can look at some of the things like this, and you could do either one or three if you wanted to on population dynamics. Number 5 on Newton's law of cooling or warming. I don't remember which one that is. Spread of disease. They only give you one. Do Hess. That's number 7. Mixtures. They give you a couple, 9 or 11. Draining a tank. Torricelli's law. That was 13. Your series circuit. That's the RC. The LR circuit they show here without the C in it. That's number 15. Falling bodies and air resistance, that's number 17. Newton's second law. And Archimedes, here they introduce Archimedes' principle here, flotation. There's not an odd in that one. Newton's second law and Hooke's law, another name here, Hooke's law, 19. What if you had a variable mass, as in a rocket? You're losing mass all the way up. That would be number 21. They didn't give the examples of all these. And Newton's law of universal gravitation, number 23. Now, again, you don't need to do any of those. It's only if you want to. There are some additional mathematical models they mentioned here. If this has any interest to you, learning theory, if you're going into education or something like that, which infusion of a drug, if you're going into pharmacology or something of that nature. The tract is something very similar to what we were doing with, they're somewhat similar to what we were doing with the catenary, the droop of a wire. There's reflecting surfaces, mirrors, and to some extent lenses. Okay, if you want to look at some of those three, 25, 27, and 29, should have answers at the back. The rest of them, discussion problems, don't necessarily. You can look at those if you'd like, but that's usually those are not in the back. We have just finished chapter 1. Now, do you have to turn any of those for your homework assignment? No, you don't, because sometime, hopefully between, I don't know, my next class gets out at 11:15. I'm going to try to grab a little bit of lunch. I have my telemedicine appointment at 2, and I have the next class starting at 5. So hopefully between 2 and 5, I will load your test and put it on Blackboard messages. That's where I'll load it. Now let me see if I can find a copy of it just to show you, or at least talk about it some. Here it is. Okay. Now, certain ones of these questions are really easy, like that first one, fill in the blank. All you're doing is taking a derivative. Okay, that's all you're doing. Don't try to make it more difficult than it is. Okay. Uh, the second one, and there were some examples like this in your text. They give you. We didn't do any, I don't think, in class, but they did in the homework exercises. They give you a y as a function, two parameter system. They have you take the first derivative and second derivative. Again, you're just taking derivatives. But then the last part says, now write that function, the capital L function, as a function of those three and set it that's equal to 0. So what is that combination of your y that they gave you, your y prime you're going to calculate, and your y double prime? What combination of that gives you 0? That's what the last part of that question is. We did do some things like that. The number 3, determine by inspection at least one solution of the differential equation. That's much easier. Don't get too bound up. It's a really simple solution, okay? But I'll let you look at it. I know we only have about 20 minutes to go, but I really need a bladder break. Can y'all stand one? Okay, let's do a real quick break. I'm going to stop the recording. I'll keep Zoom going, though there won't be anything on it. So I'll be right, and it's running again. And by the way, y'all can get up and go anytime you want to. Don't tell the dean that I said that. She was an elementary teacher, and you're supposed to ask permission to leave the room. No, I'm just kidding. But I can't, you know. But if you don't want to miss something and you really would like to have a quick break, these are long classes, 2 hours and 15 minutes is a long time, especially shortly after breakfast. If you do anytime midway through the class, approximately there or later, if you say, hey, can we take a break? I'm going to be all in favor. Okay. So we can do that. So you don't have to wait for me to say it. If you feel like you need to and you don't want to miss anything, we can take a break anytime. All right. I gone through the third problem. It's really much easier than you don't make a mountain out of a little bitty molehill here. Okay. Now, the fourth question is one of those, like we had several in class and homework exercises. Verify that this one parameter family of solution is an implicit solution of the differential equation given. And again, all you do, same technique we did before, you take the derivative. Now, this is an implicit differentiation. You can't do it explicitly. You have to do it implicitly, okay? But do that and show that it's true. Now, on problems like that, I know I haven't left enough of a blank line. So basically, you're going to be showing me your work probably on another piece of paper or something like that. Some of these you can write down in the blank easily. Others, you might need more room. Okay? For instance, that number 2. By the time you do the product rule and stuff like that, you'll find those blanks are way too short. Okay? So use another piece of paper, whatever. All right. Number 5 is a standard kind of thing. What is the slope of the tangent line to the graph of the solution? Blah 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 that passes through there. That's pretty much a something you've probably done several times before. Now, problem 6 and 7. I'll apologize ahead of time. I got them out of the material that came with the book, and I thought they looked like they would be pretty reasonable. They are pains in the neck. I have worked through them myself. It's going to take you a lot more room than you have here. Okay. Again, it's verified. Verify the indicated function is a solution, is an explicit solution for the given differential equation. You have the differential equation, you have the solution, you need to verify. I guarantee you, you cannot do it on that little line that's given. That's 6 and 7. You're going to hate me by the time you finish. Oh, I hate the book. They're the ones that came up with the problem. Number 8 is another verify. It's not quite as messy as the other, but it has its own nuances. Okay, so you'll have to do some fiddling with that. I think we did some homework exercises that were similar to that. Number 9, actually turns out to be a pretty easy thing. It's an initial value problem. It's much easier than the verification. It is some work, I guarantee you that, but it's not nearly as bad as the as some of the earlier ones. So it's all stuff we've done, or you should have been doing if you've been doing homework exercises. Some of them are a pain in the neck, and remember, you have at least a week to work on it. And the reason I say at least a week, if you have questions on it, be sure to ask those uh, on, let's see, today's Tuesday, ask them on Thursday. And that way you can clear up anything. If there's something you don't understanding, or you say, is this really as bad as it, yeah, or no, it's not nearly as bad as you're making it. You know, if you want to ask questions, you certainly can. I won't work a problem in class, but I'll do what I can to move you along that direction. Okay. If you need more time, you can certainly have it, but please do not keep this test until we're ready for the second test. You need to get it in before we finish chapter 2. But chapter 2 is a long thing. Now, while I'm here, let me say this. There are some other problems in your book that you should certainly do. You see the chapter 1 in review. These are other problems. If you didn't have enough of homework exercises to do, again, the odd number exercises to selected odd number exercises are in the back of the book. So you can do number 1 if you'd like, number 3 if you'd like, number 5 if you'd like. Any of the odds 7 through 11 if you'd like, 11 if you'd like, 15 if you like. Any of the odds 17 to 21 if you would like. 23 or 25 if you would like. Those are some similar to some that you have in the text on the test. Okay, 27 or 29 if you'd like to try those. Either 31 or 33 if you'd like to again verification problem. 35 or 37 an initial value problem. Okay, both of those. 39 is a this is getting into the stuff we did in that last section. You can do them if you're interested in doing them. It's up to you. 39, well, that's it. They just give one. That's why I didn't want to do too much on homework there because they really didn't do a lot in the review. They're not putting a lot of emphasis. So you certainly can look at that if you'd like. All right. Any questions on chapter 1? Okay. Then, okay. Okay, I'm going to put it. It's not there yet. It'll be probably sometime this afternoon or evening before I get it there, and it will be on Blackboard under um, messages. Do you know what that is in Blackboard? Okay. Well, what you do, here's what you look for. If you have you gotten to Blackboard in this class? Okay. When you're in Blackboard for this class, somewhere across the top of the page, you'll see a bar of icons. The icon near the right, not at the end, but near the right end, is one that looks like an envelope. That's the messages. Click on that and that's where it'll be. If there's nothing there yet, don't sweat. I'll get it there as soon as I can. I got it ready last night, but I was hesitant to put it out there for today because I wasn't sure we're going to finish 1.3 today. So now that we have finished this, we'll go on and start in that. I'll put it out there. Like I say, I can't do it between classes. I only have 15 minutes, and I got a doctor's appointment, a telemedicine appointment right after the second class, so I have to wait till after that's over with. I've got hopefully a couple of hours between the next 2 classes, even though I've got to get a test ready for that class, but that hopefully that won't take long. Okay, so hopefully it'll be there between 3 and 5. If it's not, it'll be there sometime this evening. Okay, good deal. Any other questions? All right. Yes. Yes. Just try to get the first test completed before you finish the second chapter. And if you look at the second chapter, you see that there are 6 sections. Okay. The first section is again one of these blah, blah, blah sections that just talks about general stuff. And finally, 2, 3, 2, 2, 2, 3, 2, 4, 2, 5 are all um, techniques of solving differential equations. Linear, first order, well, not linear, first order differential equations. 2.6 is a numerical method. That's where we're going to hit it. It's not the best. I don't know why they put it in here except just to give you an idea of what you can do with numerical methods. There are much better ones, but generally they're done with computer programs rather than do them by hand. This is one you could do by hand. All right. So any other questions? All right. 2.1. Again, one of these blah, 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 just general type things, but it is kind of an important concept, somewhat anyway. And this is talking about solution curves without a solution, which sounds sort of bizarre, doesn't it? Basically, what you're looking for is what is your differential equation doing? How is it acting? And 2.1.1 is talking about direction fields. Okay. And this is dealing with first order differential equations. And remember when we called it I think the term they used for it was normal form of writing one, that this is what it is. Well, actually, Melissa, if you do want to write this, if you see that first formula there, dy dx is equal to f of xy. You want to do that? I'll clear this out of the way. But if you don't want to, I can do it. Well, I think I can do it. Can I get say again? Okay. So if you'll write that, dy dx is some function of x and y. That is what we call I think they called it the normal form for a differential equation. Remember, the other form was a capital F of x, y, and y prime is equal to 0. That's question 2 on your test. You're going to get it into that other form, the capital F form. But this is the normal form. Your dy dx is equal to some f of xy. Okay. Now, think about what that's saying. What is dy dx? Go back to Cal 1. What was your dy dx? Anybody? Simplest definition for it. It was your slope of a tangent line, right? That's what the first thing we do with first derivatives. Slopes of a tangent line at any value x and y. So guess what we're doing with this? If you know that function in this normal form, x and y, and you know at least one point, so this needs to be an initial value problem, you might say. You know at least one point that 2, 3 is on this. This is where you're interested in finding something about this function. Well, if you know the function, some function of x and y, plug in the 2 for x, plug in the 3 for y, find out what its value is, and that's the slope of the tangent line at that point. Right? That's what dy dx is, slope of a tangent line. Okay? You can also call it a rate function. Okay? It's how y is changing with x. And this tells you that's the slope at that point, if you know a value at a point. So this then leads to what we call direction fields. Now, here, if that's a linear function, you know everything you need to know about it. Okay? Because dy dx gives you the slope, and if you know a point, you use the point slope formula, you know the whole function. However, if it's a function that's not a straight line, not a line, a linear function, has any kind of curvature or changing to it at all, you still know the value, and this was at what, 2, 3. I use the same numbers they did. Okay, I've taught from this too long, I'm remembering it. Okay, and you know at the point 2, 3 that tangent line is right on that curve. But look, just above and below that point, it's awfully close, isn't it? It's very, very close. You get too far away and the answer is not the same. But you see for a region in there, it's really close to the same value. Your tangent line is a good linear approximation of what the curve is doing, as long as you don't get too far away from that 2, x equal 2. Okay? Now, what you can do if you really have a lot of time on your hand, or you have a computer program that'll do it for you, that's better. You can do a direction field. I think that's what they call it. Yeah, a direction field. You can calculate for any ordered pair of that function. If you know the function, any ordered pair, you can calculate it. And then start at any position you want to. Up here, down there, follow the direction field. Follow what the slope is at that point. Positive slope go up, negative slope down, zero slope is horizontal. You can follow that thing. And then you have a decent idea of about where that function is going. You may not know the exact solution, but you have a really good idea. Okay? Just starting at slightly different values here, you see the function can take off and do all sorts of different things. That's using what they call a direction field. All right? Well, that's leading to example 1. And I have a feeling we probably can't quite get example 1 done before the time runs out. So we'll begin next time with example 138. Okay? And the only person we're missing today is Billy. We didn't see Billy today. Hopefully I'll get you in the roll book by next time. I had a student yesterday while I was teaching asking if he could get in a class. And wait, registration was a long time ago, but another instructor was letting him in. So into her class, I didn't mind. Uh, so I'm kind of waiting until they finish all the additions and deletions to the classes. So hopefully you'll be in the roll book next time. And you'll feel much better there, won't you? We didn't get enough done for any homework exercises in 2.1, so don't sweat that. But we'll pick up and go from there next time. Any questions? And again, your deliverable for today's class, and it doesn't have to be done by Wednesday, but just whenever you can get it done, will be the first test. And believe me, it's going to take you a while, so start working on it. Dawson's been in some of my classes before, and take-home tests sound like a fun thing, don't they, Dawson? But they don't always turn out that way. Well, Corbin and you and demonstration, I'm going to blank on your name. Cole, I think have also been in summer classes with me before. Ricky, you're in another class right now. Okay. So anyway, this will take a bit to work, but hopefully you'll learn something in the process. All right, good deal. Any last questions before I end it all? Okay. All right. Have a good couple days. We'll see you on Thursday. Ending the meeting now. Thank you, Melissa.